Following the presentation of the CCM strategy given by Gerd Rietveld, I will now present to you the work of the BIPM electricity laboratories. This was also already introduced by Gerd, and as you will see, the activities and the projects of the electricity laboratories are in fact quite well aligned with the CCM strategy. The most important part of our work are the measurement services which we provide for the NMIs of member states. These take two forms. We organize measurement comparisons of national electrical standards. These lead to measurement reports, comparison reports, and to publications in the BIPM key comparison database. And you will see some examples of this in the coming slides. For those NMIs which do not realize themselves electrical units, we provide calibrations of national electrical standards, for which they then get, of course, calibration certificates. In addition to the measurement services, we have some development activities and projects. These are oriented towards developing new comparisons and improving our facilities and developing new facilities. Some of them were already mentioned by Gerd. So we prepare a new comparison of Josephson voltage standards for sinusoidal signals, so at AC. We are characterizing graphene quantum Hall samples to use them in a future more complex quantum Hall system, and we're developing a calculable capacitor and a Kibble balance. Let me talk first about our measurement services, about the comparisons. So we have 5 ongoing BIPM comparisons. 2 of them are on-site comparisons of quantum standards. What this means is that we are traveling with the BIPM transportable quantum standards to the site of an NMI. We set our system side by side with theirs and we compare them directly. We do this for Josephson voltage standards for 2 fixed voltages at 1.018 volt and 10 volts. And the second comparison is of quantum Hall systems, where we have 3 measurements: the calibration of a 100 ohm resistor against the quantum Hall resistance standard, and 2 1:100 resistance ratios. In addition to the on-site comparisons, we have 3 bilateral comparisons which use conventional transfer standards which are provided by the BIPM and which are characterized by the BIPM. We do this for Zener voltage standards. At the same 2 fixed voltage levels as the comparisons for resistors at 1 ohm and 10 kilo ohm, and for capacitors at 10 picofarad and 100 picofarad. So let's look at some more details at the on-site comparison of Josephson voltage standards. So as I said, this is a direct comparison in the laboratory of the participating NMI between the BIPM Josephson voltage standard and the NMI's Josephson voltage standard. Typically, this takes about 1 week. During this time, the BIPM staff stays on site. You see one picture here on the left, the BIPM system with a BIPM operator, and on the right side, the NMI system with one of their staff members. And what they're actually doing is shown here. So they both have a Josephson voltage standard. They are connected in opposition. So here by the red line, the 2 high potential sites are connected directly. And between the low potential sites, we're measuring the difference voltage with a nanovoltmeter. This then allows to determine the differences between the measurements, or between the realization of the 2 Josephson voltage standards for the same nominal voltage of either 1 volt or 10 volt. This graph here is taken from the key comparison database. It shows all the measurement results which we have obtained over many, many years, and you see all the NMIs which we have visited. Typically, the uncertainties are at the level of 5 nanovolts. The differences are, in general, slightly smaller than that. So we're talking about parts in 10 to the 10 here. Typically, we do this twice per year. Now, what we've quite often found is that this collaborative work between the BIPM staff and the local staff leads to some improvements of the participants' Josephson voltage standards. So Gerd Rietveld mentioned that we do some CBKT work. So these comparisons have, in fact, an aspect of knowledge transfer. And this you can see here. For some comparisons where I have not identified the institutes, you see in blue the initial result, which was obtained directly at the start of the comparison, and at the end of the week, the final result in red. And you see that there are, in some cases, quite dramatic improvements either in the value or in the uncertainty, and in many cases, even still quite some substantial improvements. These pictures show you some impressions from these on-site comparisons. You see the different steps from the work in the laboratory, trying to obtain a good result, discussions of the results, trying to understand why maybe at first it did not work as well as expected, and then finally posing proudly in front of the camera when the good result has been obtained. The second on-site key comparison is of Quantum Hall resistance standards. This was started a few years ago in response to an explicit request from the CCEM, and typically also we do this twice per year, except around 2018, 2019, we had a very busy period with 4 comparisons in Asia, so very far away from us, within 12 calendar months in Japan, in Korea, in Singapore, and in China. The measurements are shown here on the right side. The green boxes represent material which is brought by the BIPM, and the blue boxes and blue arrows represent material measurements made by the NMI. So the first measurement is the value of a 100 ohm resistor calibrated against the second quantized Hall plateau of a Quantum Hall standard. This measurement is done with BIPM equipment, with the NMI equipment. And then there are 2 resistance scalings, resistance ratios from 100 ohm up to 10 kilo ohm, down to 1 ohm using a BIPM bridge and the NMI's bridge. The results of these comparisons then, they go into the key comparison database, and this is the 3 graphs for the Quantum Hall comparison for the 3 measurements. So here the resistance calibration, the 100 ohm calibration, and the 2 1:100 ratios. Here now the uncertainties are typically 5 parts and 10 to the 9 with differences which are in general smaller than that. Now, as I said in the introduction, in addition to the 2 on-site comparisons, we have 3 comparisons using the exchange of traveling standards. Sorry. So what you see here is the comparison of Zener voltage standards, just result for 10 volt. There's a second graph on the KSDB for 1 volt, which I do not show here. Then we have the resistance comparison, and here I just show the 1 ohm result. There's a second option to do 10 kilo ohm comparisons. And then for capacitance, and here you see the result for 100 picofarad. What you will notice is that on the graphs there are red dots. Well, these are the BIPM comparisons, and there are colored dots. These are comparisons made by RMOs, Euromet, APMP, GulfMet, SIM, and these are linked to the BIPM comparisons by the participation of BIPM in these regional comparisons, which then allow us to draw everything on the same baseline. For institutes which do not have their own unit realizations, we provide calibrations of electrical standards. These are basically exactly the same quantities for which we do the comparisons. So in voltage, you see the 2 levels of 1.018 volt and 10 volts, then 1 ohm, 100 and 10 kilo ohm, and 1 picofarad, 10 picofarad, and 100 picofarad. For Zeners, typically there are 3 to 5 comparison calibrations per year, and for the resistance and capacitance surfaces, we're around 30 certificates per year. You see the statistics here in the graph. The blue bars are for Zener voltage standards, red as resistance, and yellow as capacitance. What you can observe is a slight increase in the demand for resistance and capacitance. This is mainly due to the increasing number of member states over the recent years. And if you look at the last 10 years, you see also an increase for calibration requests for Zener voltage standards. Now, in the second part of my presentation, I'll talk about our development activities, and I start with the development of a future calibration of a comparison of Josephson voltage standards. The comparison I've shown you before, this was for 2 fixed voltage levels, 1 volt, 10 volt. So we're now preparing a comparison for sinusoidal signals in the range up to about 1 kilohertz. So the comparison scheme will use differential sampling. The measurement will be the RMS value of an AC source, which you see here. And this is put in opposition with the stepwise approximated sine wave from a PJVS, and then the difference between those signals, which resembles to what you see here. This is measured with a sampling voltmeter. These measurements are done by the NMI with its equipment, by the BIPM with a BIPM equipment, which will again be brought to the laboratory of the NMI. Then both institutes can reconstruct the sine wave from the sampled measurements and determine the RMS values of the source. Now, to be able to run such a comparison requires quite a lot of preparative work, and these are the studies we've done so far. Of course, to be able to do this, we need a very high quality AC source, which serves as a sort of transfer standard between the two sampling experiments. This source needs to have a high stability of amplitude or phase and a good spectral purity to eliminate the aliasing effect. Now, of course, a programmable Josephson standard, when it produces a stepwise approximated sine wave, has transients between each of the voltage steps. During the transients, the voltage is not quantified, so one cannot do a measurement during this phase. This is the reason, or one of the reasons, why we need a good synchronization between the three instruments. We also need good synchronization, of course, between the AC source and the PJVS so that they're both in phase. And this, of course, minimizes the difference voltage we measured. The samplers have been investigated, their properties like bandwidth, gain and linearity. And of course, software is important because one needs to reconstruct the AC waveform by fitting a sine wave. And one needs to apply a correction for the aperture time of the DVM because during the measurement time, the signal is not constant. And statistics needs to be done. So we need to determine the repeatability of the measurements and to determine uncertainty for the RMS value of the fundamental of the AC source. A lot of studies were done on these different effects with support from many NMIs in form of collaborations and pilot studies. NIST participated, NMIJ, CRIS, PTV, the NPL, VNIM, NMIA, VTT, and XENAM. And finally, a technical protocol was proposed and approved earlier this year. We plan to upgrade our Quantum Hall resistance standards, and what we are planning to do is to use it in the future with graphene samples. Therefore, we are characterizing these samples. Graphene samples will allow to use a Quantum Hall standard at much lower magnetic fields and higher temperatures as we do at present. Presently, we use magnetic fields of a little bit more than 10 Tesla and temperatures below 2 Kelvin. With a graphene standard, we could operate below 4 Tesla and at temperatures of liquid helium 4.2 Kelvin. And this would, of course, allow to make a much more compact Quantum Hall system, which is important because we are traveling with these systems. The present system weighs more than 1 ton. So we hope to be able to have a much more complex and easily transportable system in the future, which would also allow to operate at reduced operation cost. And the ultimate goal is to integrate such a system in a cryogen-free system, which would eliminate completely the need for liquid helium, which has become very expensive and very difficult to obtain in some parts of the world at present. Since 2020, we have characterized 2 types of graphene samples. One set of samples were commercial samples from graphene waves, which are based on NIST technology. And we also had samples developed by PTV in the framework of a Euramet project, GIGS, which stands for Graphene Impedance Quantum Standard. We also would like to test other sources when they become available. But already now, so far, we have obtained very promising results. What you see here are comparisons between the PTV graphene sample and the conventional gallium arsenide samples, which we use at the BIPM since a long time. You see the difference, and so between 2 lines, we're having 2 parts and 10 to the 9. And you see that at magnetic fields above 3.5 Tesla, we have agreement within 2 parts and 10 to the 9, which shows that the graphene sample is indeed well quantized at these quite low fields. And these measurements were done at 4.2 Kelvin. We are developing a calculable capacitor, also called Thompson-Lampard capacitor, because the operation is based on the Thompson-Lampard theorem. At the heart of the calculable capacitor, there are 4 cylindrical electrodes, which are placed at the corners of a square, a perfect square. In between the electrodes, there are 2 guard electrodes shown here in green. They define the effective electric length of the capacitor. When we now, one of these electrodes will be mobile, so if we change its position by delta L, we increase the effective length of the capacitor, and the resulting capacitance change is then given by this very simple equation. It's just the electric constant, the logarithm of 2 pi, which are all very well known. And the only thing which actually needs to be measured is the length change. This is done by interferometry. We get a capacitance change of 2 picofarad per meter. Now, of course, we will not build an instrument which is so long that we can displace the electrode by 1 meter. In reality, the displacement is 20 centimeters, and this gives a capacitance change of 0.4 picofarad. Now, why is this useful? You can see this on the left. You see here our traceability scheme from the Quantum Hall resistance, where we use the second quantized plateau, 12.9 kilo ohm. Then we go through a series of bridges operating at a DC or very low frequency, around 1 Hertz. We have a multi-frequency quadrature bridge, which allows us to calibrate capacitors. And then we have a capacitance bridge, which brings us down by 10:1 ratios to 10 and 1 picofarad, which are the values which you use most. So you see the chain is very long, which builds up some uncertainty. And of course, the calculable capacitor is a impedance standard, a primary impedance standard. So we would then get traceability directly at the level of 1 picofarad, which should allow to obtain smaller uncertainties. We have built such a system already quite a number of years ago. This was a collaboration initially with the NMIs of Australia. We did some first measurements some years ago, the blue points here. We changed then at one point the source for the interferometer laser, and you see that we got quite good agreement with what we had before, but we were 2.7 parts in 10 to the 7 away from the expected capacitance value, which was at that time based, of course, on the quantum Hall resistance. And it is very likely that this was due to imperfect alignment, which in fact we had at that time. And after a break of some time, we have now taken up this work again. We're at present working on a careful alignment of the electrode bars. This needs to be done at a level below a micrometer. We need to adjust very carefully the diagonal spacing between the bars, the lateral spacing, the skew angle. So what this means is that in the top plane and the bottom plane, the positions of the bars or the ends of the bars should be superimposed and not rotated with respect to each other. And finally, I'll talk about the development of our Kibble balance. This is an instrument for the realization of the kilogram. You see on the left the instrument sitting on a big concrete block with a vacuum system partly opened. In the center, you see some of the details of the system, the suspension, which holds a coil hanging in a magnet. And on the right, the operating room with one of the operators. Now, why I'm talking about the Kibble balance here, since that's a presentation about electricity laboratories, and of course the Kibble balance is most interesting for Mars. Well, Gerhard Riedfeld said it already, the Kibble balance makes use of the quantum Hall resistance standards and the Josephson voltage standard. It cannot operate with them at high accuracy, at small uncertainty. I'm not going to explain here how a Kibble balance works. I'm just saying that basically it compares the weight, m times g, of a test mass, of an unknown test mass against electromagnetic force on a current carrying coil hanging in a magnetic field. And the electrical quantities on the right side on this current carrying coil magnetic field, they are measured with electrical quantum standards. If you want to learn more about that, there is an e-learning program on the BIPM website. If you go to the address shown here, elearning.bipm.org, and there's a course on the realization of the kilogram and the dissemination. With this instrument, we've participated in the first ever CCEM key comparison of realizations of the new kilogram definition. This was started in 2019 and finished in 2020. In fact, I was also the organizer of this comparison. Here you see the result from the BIPM Kibble balance. It's a good result. It's not yet our final uncertainty. We plan to reduce this by a factor of about 2. And at present, we're participating in the second CCEM key comparison, which is now nearly completed. And this brings me to the end of my presentation. Thank you for your attention.